Hi all, and welcome back to the second lecture in this postgraduate mass spectrometry series. In the first session, we revised some basic mass spec concepts, such as how an ion moves in electric fields, the basic design of a mass spectrometer and the role that the mass analyzer subsystem plays, and then we looked at some of the features, benefits and disbenefits of electron ionization mass spectrometry. In this lecture, we'll go on to look at specific mass spectral features and measures. As was discussed in the first session, one of the key outputs of any mass spectrometry analysis of a sample is likely to be a mass spectrum. So using this spectrum as an example, let's look at some of the key features. In the last session, we discussed the axes, the mass and intensity axes. Now we're going to begin to look at the spectrum itself. I expect that the most obvious feature is that it contains peaks, and it's the presence, position and intensity of these peaks that we use to determine if a particular compound is contained in our sample and to work out how much is there. So we're going to spend quite a bit of time in this session looking at measures of peaks in mass spectra. But first, there's something else in this spectrum we need to investigate. If you look over to this region of the spectrum, there aren't any peaks, but it's not empty, there is data there. We call this kind of background signal the noise. If we zoom in, we can see it in more detail. Noise is a normally unwanted random signal that you find in almost all real data, and which can make the true signal more difficult to identify. Because of this capacity of noise to contaminate or obscure the real signal you're looking for, it's very important to consider noise in any scientific instrument, including in mass spectrometers. So before we look at the peaks, let's look at some of the aspects of noise in mass spectrometry. Here are two example mass spectra that both contain exactly the same signal. In both spectra, the signal has the same intensity. So are both these spectra the same quality? Well, clearly they're not, because in the lower spectrum we can see this additional peak, whereas in the top spectrum it's obscured by the noise. This is why we often describe peaks in mass spectrometry not by their absolute intensity, but by how much bigger than the noise they are. And we call this measure the signal-to-noise ratio. As the S/N symbol suggests, to calculate the signal-to-noise ratio, you divide the signal intensity by the noise intensity. By considering the spectral quality in this way, the bottom spectrum has a signal-to-noise ratio twice as high as the top spectrum, and that explains why we can see that second, smaller peak. If you've collected a mass spectrum and you can see that the signal-to-noise ratio isn't high enough, what can you do? Well, you might be able to increase the signal by making the sample more concentrated or by injecting a larger aliquot. But because the noise is random, there is another option, whereby we can reduce its impact by averaging multiple measurements or by measuring for longer. Take this spectrum on the right. This is an example mass spectrum showing two peaks with no noise. Now, let's assume that I record a single mass spectrum of this signal. Here we can see the larger peak is easily visible, but the smaller peak is so obscured by the noise that you couldn't be confident that it was really there. But if I recorded two spectra and then averaged them together, now you can see the little peak has become slightly clearer. If I average 5 spectra, then that small peak becomes clearer still. And if I was to record 10, 20, 50, or 100 spectra and average those, you can see that the quality of the signal gets better and better. The reason why this approach improves the signal-to-noise ratio is that the noise is random. So for any given point, in some spectra the noise will be positive, and in the others it will be negative. So over time it tends to cancel out. On the other hand, the signal is always there, so it isn't affected. This cancelling out effect of the noise means that, as a general rule, the signal-to-noise ratio in a spectrum will improve by the square root of the number of spectra you've averaged, or by the increase in the length of time you average the spectrum over. So if I average 4 spectra instead of 1, I can expect the signal-to-noise ratio to approximately double. How much longer should I average a mass spectrum for if I want the signal-to-noise to improve by tenfold? So we've discussed what noise is, and the importance of measuring spectral quality using the signal-to-noise ratio, and how averaging can improve this. But if we want to actually be able to calculate a real signal-to-noise ratio, we need to have some way to measure the noise level. In fact, this is such a fundamental concept, you'd be forgiven for thinking that there must be some specific way to do this. But surprisingly, there isn't. If you review the literature, there is a wide variety of different measures of the noise intensity that are chosen. And here's a list of some of the more common ones. Some people mean the root mean square of the noise, or the average noise, or the average noise envelope, where this can refer to the mean noise maximum minus the mean noise minimum over a particular spectral region, the length of which can be varied. Or alternatively, the mean of the local spectral maxima in the noise, but where the definition of local can also vary. One very common approach is based on the fact that the noise should have some statistical distribution. So one example of a measure like this would be the noise mean plus some multiple of the standard deviation of the noise. One of the tasks that we will undertake in the session will be to take this specific noise region and calculate some of these different measures of noise. That way we can begin to understand what the differences between them really are. But because it's important to discuss, here's a spoiler alert. If you calculate the noise levels by all these different methods, you actually get very different results. And the noise level also isn't necessarily constant across a spectrum. So how do you interpret a noise level? What this means is that a measure of the noise shouldn't be taken as a precise measure, but should really only be interpreted as a guide. And by and large, it is generally only appropriate and necessary to give the signal-to-noise ratio in a mass spectrum to the first significant figure. If you're ever required to present a noise measurement yourself, you should always state exactly how you calculated it. One other thing to consider is that both peak height and noise amplitude are measured relative to the spectral baseline. In the examples I've used so far in this presentation, the spectral baseline has always been 0. But in real spectra, this isn't always the case, and is actually a common problem in, for example, Multitoph mass spectra, a class of instrument we'll cover later in this course. So in real spectra, it may be necessary for you to correct for any baseline deviation before you can go on to calculate peak heights and noise levels. However, the methods used for this kind of baseline correction are quite complex and are not something we'll be able to cover in this course. You can, however, follow the link here to go to the paper where this specific method is described. So now we can go back to this slide and add some extra detail onto our mass spectrum. So far we've covered the concepts of the axes, the noise, and the concept of the baseline. And now it's finally time to start looking at some aspects of the peaks themselves. The first peak measure we'll look at is the peak resolution. The peak resolution describes how narrow the peaks are in a mass spectrum. In many instruments, the peak width is not constant across the spectrum, but increases by some function of the mass-to-charge ratio. Therefore, the peak width alone is rarely used as a measure of the quality of the spectrum. Instead, we calculate the resolution as the mass of the peak divided by the peak width, where the width of the peak is measured at the level that is half the peak height. This is usually described as the full width half max. In this example, the peak has a mass of 104 and a full width half max of 0.5, so the resolution can be calculated as 208. Another commonly used measure of the peaks in a mass spectrum is the resolving power. This is a measure of how well two peaks can be distinguished. At first glance, the equation for resolving power looks identical to that for resolution, but the difference is in what the delta M stands for. For resolution, it was the full peak width at half the peak maximum, but for resolving power, it's the mass difference between two peaks of equal height where the valley between them reaches some fraction of the peak height. Commonly, this valley height is 10%. The value for M can be taken from either of the two peaks. So for this example, if we use M from the larger ion, that means M is 105, and the mass spacing between the peaks is 1 Dalton. Hence the resolving power is 105. And as for resolution, resolving power is unitless. One special case to consider is if the two peaks are separated sufficiently that the valley between them reaches as low as the baseline level on either side of the peaks. Then these peaks would be said to be baseline resolved. The definitions that I've just provided for resolution and resolving power are the ones that should be used in this module, and I've separated them in this way so as to highlight the differences between the two measures, one that refers to individual peaks, and the other that is concerned with distinguishing two peaks. However, while the meanings of resolution and resolving power as I've described them are common, and they are described as such in some IUPAC references, these definitions aren't universal, and there does remain significant controversy. Both the IUPAC and others have also described resolving power as I've just described resolution, and resolution as I've just described resolving power. In some other references, you can also find resolving power defined simply as the mass difference that can be resolved. So it's fair to say that this area has not yet been standardized to a satisfactory level, and many people still use resolution and resolving power interchangeably. So you could argue, does it really matter? Well, yes, it does up to a point because it affects how people interpret what you write. My advice would be that if you ever need to report some measure of the peak width, be sure to define what measure you are using, as this will avoid all doubt. The next important measure of a peak in a mass spectrum is the mass accuracy. This describes how close the peak position is in a spectrum to the theoretical mass of the ion assigned to it. If the predicted mass of a potential formula is too far from the mass spectral mass, then this assignment may not be correct. Or alternatively, if you know that the assignment is correct, but the mass error is large, then this implies that the mass calibration of the mass spectrum must be inaccurate. Either way, the mass error is telling you very important information. There are two common measures of mass accuracy. The first of these is the absolute mass error. This is calculated as the mass difference between the mass of the peak in the spectrum and the exact mass of the ion derived from the ionic formula. Because the mass error in most instruments should be small, this absolute mass error is usually expressed in millidaltons instead of daltons. The second common way to express the mass error is in parts per million. The formula for this is the absolute mass error divided by the formula mass and then multiplied by 1 million. We'll practice both of these measures in the workshop. We also need to have a more in-depth look at isotopic distributions. If we were to record a mass spectrum of carbon atoms, we would see two peaks in the spectrum. A big peak at exactly 12 daltons, and a smaller peak at the mass of carbon-13. The intensity of the smaller peak would be about 1% of the intensity of the main peak, because it would reflect the natural relative isotopic abundance of carbon, where carbon-12 accounts for approximately 98.9% of naturally occurring carbon, and carbon-13 accounts for approximately 1.1%. Remember, you can use the SIS website, linked from here, to find a useful reference to all the naturally occurring stable isotopes and their relative abundances. If we were to plot the mass spectrum of clusters containing 2 carbon atoms, now we would see a mass spectrum containing 3 peaks. The largest intensity and lowest mass peak would correspond to the mass of a cluster containing 2 carbon-12 atoms. The highest mass but lowest intensity peak would correspond to the mass of a molecule containing 2 carbon-13 atoms. And in the middle would be a peak coming from molecules containing 1 carbon-12 and 1 carbon-13. But how can we calculate what the relative abundances of these peaks should be? Well, you might intuitively think that because there's only 1 carbon-13 atom in the clusters associated with the middle peak, that the relative abundance of that peak would match the relative abundance of carbon-13. But this isn't the case. This comes from the fact that there's only one way to make a 2-atom molecule where both the atoms are carbon-12. Both of them have to be carbon-12. And at the other end, there's only one way to make a molecule containing 2 carbon-13s. Both have to be carbon-13. But for the middle peak, there's 2 ways to make this molecule. You can either have carbon-12, then carbon-13, or you can have carbon-13, then carbon-12. So the probability of a molecule with this mass is actually twice as high as you'd expect. And we can extend this idea of the intensities of peaks in isotopic distributions corresponding to the probability of that combination of isotopes to larger clusters. Indeed, clusters of any size. But in order to calculate the relative abundances of the peaks, we need to be able to calculate the number of different ways that each cluster can be formed. Luckily, this is a branch of maths that is well known, binomial theorem. Binomial theorem was covered at GCSE level or below, so you should have covered this area when you were at school. If you can't remember it well, here's a link to some GCSE revision material. You should probably have a look at this before the workshop. Definitely so if you don't remember why I'm showing Pascal's triangle on the screen just now. But for the minute, let's just go through a simple example using the idea of coin tossing. What's the probability of getting 1 head and 1 tail if you toss 2 coins? And think about what we were discussing just a moment ago. With 2 coins, you can have a head and then a tail, or a tail and then a head. So there are 2 ways to get this combination, and therefore it will be twice as common as it would be otherwise. Now we can get this multiplier from the relevant row of Pascal's triangle. In this case we have 2 coins, so we use row 2 of Pascal's triangle. The top row is row 0. Reading across the row, we can see that we have only 1 combination that will result in 2 heads, 2 combinations that give 1 head and 1 tail, and 1 combination that gives 2 tails. So what about a larger number of coins? What's the probability of getting 3 heads if you toss 5 coins? Well, now we're dealing with 5 coins, we need to use row 5 of Pascal's triangle. Note, you can always get the row number from this diagonal. So on this row, which coefficient to use? Well, the coefficient for 5 heads would be 1, 4 heads, 5, and 3 heads is 10. So the multiplier we need is 10. And now we can do the calculation. We have the probability of a head, that's 50% or 0.5, raised to the power of the number of those we have, 3. And we have the probability of a tail, also 50%, raised to the power of the number of those. Well, if we have 3 heads out of 5 coins, then we must have 2 tails, so we use the power of 2. And finally, we multiply those together, and also multiply them by the 10 we got from Pascal's triangle to give us the final probability, about 0.31. Now, having done that calculation for 5 coins, we can easily adapt it to work out the probability of getting 3 carbon-12s out of 5 carbons. The calculation is identical, except that we've put in the probabilities of carbon-12 and carbon-13, and these are just the natural abundances. So the calculation now reads, the probability of a carbon-12, that is 0.989, raised to the power of the number of those we have, 3. And we have the probability of a carbon-13, that's 0.011, raised to the power of the number of those. And as before, if we have 3 carbon-12s out of 5 carbons, then we must only have 2 carbon-13s, so we use the power of 2. Finally, we multiply those together, and also multiply them by the 10 we got all the way back in Pascal's triangle, to give us the final probability, about 0.00117, or 0.117%. If we look at the mass spectrum we'd get for 5 carbon clusters, here's the monoisotopic mass, all carbons as the same carbon-12 isotope. The next peak shows the abundance of clusters containing 1 carbon-13. And if we zoom right in, here's the peak corresponding to clusters containing 3 carbon-12s and 2 carbon-13s, which shows the intensity we predicted. So there are 2 takeaway messages we should get from this. Firstly, that you can use binomial theorem to calculate the relative abundances of elemental clusters of ions containing different combinations of isotopes. And secondly, that in the resulting mass spectra, the peak height in isotopic distributions is related to the probability distribution of the various combinations of isotopes. Of course, we will practice these calculations in the workshop. When we only have 5 carbons, the peak corresponding to when they're all carbon-12, the monoisotopic peak, is the most intense, because that combination has the highest probability. But the more carbons we have in a molecule, the lower the probability of none of them being carbon-13. By the time we get up to 200 carbons, the most probable combination includes 2 carbon-13s, and the monoisotopic peak is no longer the most intense peak in the distribution. Once you start looking at biomolecules like proteins, you see very wide isotopic distributions, and the monoisotopic peak may be so small that you can't see it. In this example, insulin, the most abundant peak in the distribution, is 7 Daltons heavier than the monoisotopic peak. Now this might be due to the molecule having 7 carbon-13s, but this protein contains more elements than just carbon, and most of these also have more than one stable isotope. So some fraction of this peak's intensity also comes from combinations involving these heavy isotopes too. And there's a shorthand used to label peaks like this. We tend to call the monoisotopic peak M or A, and the heavier isotopologue peaks by the number of extra neutrons they contain, so M or A plus 1, 2, 3, etc. In this nomenclature, the most abundant isotopologue in this distribution is the A plus 7 peak. A and M are used interchangeably depending on the reference you're looking at. And also, as I'm using the term isotopologue, now is a good time to consider the meanings of the 2 terms isotopologue and isotopomer, as they're often confused and used incorrectly. So for this explanation, I'll use ethanol as a simple example. On this slide, all the atoms shown are the most abundant isotopes of a particular element, so carbon-12, hydrogen-1, oxygen-16, except for one of the hydrogens that is a deuterium. So in this case, all these ethanol molecules are isotopologues of each other. They all have the same elemental formula and all contain exactly the same combinations of isotopes, specifically meaning the numbers. In this case, they're all the most abundant isotope except for one deuterium. But you can also see that the deuterium atom is not in the same location on all the molecules. On this top one, it's on the methyl group. In the middle, it's on the methylene group. And down at the bottom, it's over here on the methyl group. Now, if we were moving a functional group around different locations in a molecule, we'd call the different resulting molecules isomers of each other. In this case, we're moving around the positions of different isotopes within a molecule, so these are isotopic isomers, and we abbreviate that to Isotopomer. So as a reminder, isotopologue means all ions that have the same ionic formula containing the same numbers of isotopes irrespective of their structure, whereas isotopomer means a specific distribution of isotopes within molecules of exactly the same chemical structure. You may well find these 2 terms mixed up in the literature. So now let's jump back to this slide so we can use it to go through some common definitions of specific features in isotopic distributions. This tallest peak is the most abundant mass. This peak over here is the monoisotopic peak, and we've encountered that before, where all elements are in their lowest stable isotope. The average mass is the mass we would get for the protein if we found the centre of mass of the whole isotopic distribution, or alternatively if we'd calculated the mass of the protein based on the molar masses of the elements instead of their isotopic masses. And importantly, you can see that the average mass doesn't actually line up with any of the actual peaks in the spectrum. So this is another reminder not to use the molar mass to calculate ion masses in mass spectrometry. There is another mass you might encounter, and that's the nominal mass. So the nominal mass is when you calculate the molecular mass using the nominal masses of the elements, so where every element is rounded to its nearest integer. So carbon's still 12, but hydrogen becomes 1, oxygen becomes 16, and so on. If we calculate the mass of the protein in this way, then the nominal mass is way over here, completely outside the isotopic distribution. So this is why, although the nominal mass is okay to use for estimating the mass of small molecules, it can't be used for large biomolecules like proteins. For these, you really do have to use the exact masses of the elements. And while we're here, we should have a quick look at what happens if we were to analyse the same protein at different resolutions. If we looked at this molecule as a singly charged ion on a good benchtop time of flight mass spectrometer, we might see its distribution look like this. But if we were to use older or lower specification instruments, we wouldn't get such high resolution. So if we analyse the same ion through an older generation time of flight, we might see the distribution look like this. And you can see the peaks are no longer baseline resolved, and they're starting to overlap. On a really modern quadrupole instrument, the resolution would be even lower. And on an old ion trap instrument, where we might only have a resolution of 5000, the entire isotopic distribution might appear as a single hump. In this case, the top of the single peak actually does line up with the average mass you get from calculating the protein mass using the molar mass of the elements. But this is the only situation where you can use the molar mass in mass spectrometry. The binomial method of calculating isotopic distributions only works for clusters or compounds containing a single element. In fact, a single pair of isotopes for that single element, because you couldn't, for example, use this binomial method for an element containing 3 stable isotopes like oxygen. So what method can we use to calculate the isotopic distributions of molecules? Yes, there is software to do this, but a manual method can still be useful. And on the next slide is a video demonstrating one of these methods. Now, having watched that video, use the grid method to calculate the isotopic distribution of aspirin. If you use the grid method directly, you'd start with one pair of atoms and produce a grid for them. Then the result from that grid, you could add one extra atom on and produce a new grid, and adding atoms on one at a time, each with their own grid, building up the answer as you go until you get the complete isotopic distribution. But obviously that's very slow. So you can use a shortcut. You can use the binomial method to calculate the isotopic distributions of all the carbons and also all the hydrogens individually, and then you can combine them together in a single grid and then add the oxygens individually, and that should be much faster. Try to complete this problem and bring your answer to the session. I've also made an HTML5 version of this video. The benefit of watching the presentation in HTML5 mode is that you get to go through it at your own pace and answer questions and problems as you go along to help you understand the material. To find the HTML5 versions, go to the Kilgour Lab website at www.kilgourlab.com and then go to the Teaching Resources page. On there you'll find a whole variety of resources to help you learn about mass spectrometry. I hope you enjoy them. So that completes the second lecture in this postgraduate mass spectrometry lecture course.